Hello friends. In this video we're going to continue our discussion of the entropy change associated with the freezing of supercooled water. In the last video we calculated the entropy change for the freezing of water at -5 degrees Celsius by constructing three reversible paths that led from the liquid at 268 Kelvin to the solid ice at 268 Kelvin, calculating the entropy for each of those paths, adding it together to get the overall entropy for the system, and we found it was negative. Now, it's not surprising since the most important factor in the determination of the entropy change for freezing involves the exothermic process of freezing itself. And the exothermic process, meaning heat is released, would result in a negative entropy change. So is this a violation of the second law of thermodynamics? And the answer is, of course, no, because we only considered the entropy change for the system and not for the universe. Because the second law of thermodynamics says that an entropy change for an isolated system, the universe, for example, must be greater than or equal to 0. So if we've considered the system and it's exothermic, it's releasing heat. Where's that heat going? It's going into the surroundings. So it's not an isolated system. We have to consider the surroundings, and we have to consider the entropy change for the surroundings to figure out the overall entropy change for the universe. All right. So we're going to do that in this particular video. So we start with the surroundings and the definition of the entropy change for the surroundings. Now, when you look at this, all right, you'll see that it's delta H for the system. So this would be the enthalpy change for the system, all right, which, as I said, was an exothermic process in this freezing. We have to change the sign because, for example, if it's exothermic for the system, it's endothermic for the surroundings. So we multiply it by a negative sign there because we're switching the sign. And that would give us, dividing by the temperature, and this would be for an isothermal process. It is a phase transition. It's isothermal. So that we can calculate the entropy change for the surroundings with that. Now, you may be asking yourself at this point, but wait, doesn't entropy calculating delta S require that we devise a reversible path? And yes, it's true for the system, but not for the surroundings. In the case of the surroundings, we can take the enthalpy change for the transition at 268 kelvins in this case and use that directly. The simplistic assumption here, rationalization, if you will, is that the surroundings are so much larger than the system that any change in the surroundings is reversible. Now, you could debate that, of course, but this is the calculation that we're doing to show the entropy change for the universe, and it does give us the result that we would expect in the case of supercooled water, because we certainly would expect supercooled water. It's going to freeze. I mean, if it's below 0, it's going to freeze irreversibly. So that's what we're going to do. So the first thing we have to do is figure out what delta H is for the system. Now, one assumption might be that the enthalpy change associated with the freezing at 268 is the same as it is at 273. It's not a horrible assumption because it's a small temperature change, and for small temperature changes, typically enthalpy changes for processes don't change a whole lot. They're relatively independent temperature over small ranges. But in actuality, it's not hard to calculate the enthalpy change at 268. And so why not go ahead and do that if it's not hard, so we have a more rigorous result. And so that's what we're going to do. We're going to calculate the enthalpy change at 268 based on what we know at 273. Okay, and so we know the value 273 is 6,008, or negative 6,008 since it's exothermic. It's negative 6,008 joules per mole. And so that's what we would have here. And then delta Cp is a difference in heat capacity between the liquid and the solid. And so again, we're making an assumption here. This is basically a rule, a law that we learned about early on when looking at enthalpy changes associated with chemical reactions, that if we assume that delta Cp is relatively independent temperature, and that is a pretty good assumption for 5 degrees, then we just take delta Cp and multiply it by the temperature change itself. Okay, and again, delta Cp, just to be specific here, is going to be the heat capacity of the ice minus the heat capacity of the liquid. All right, so that's basically what that's going to be. So we just need these values to plug in. Just becomes a plug and chug equation. It's everybody's favorite kind of calculation. We just plug those numbers in. Here again is the enthalpy change associated with 273, the exothermic process. Delta Cp is negative 37.54. It is negative. The heat capacity of ice is less than the heat capacity of the liquid water. And that's usually the case. The solids are going to have a lower heat capacity than liquids because solids have fewer degrees of motion, fewer degrees of freedom when it comes to motion. Those molecules in ice in the solid are kind of locked in place. They're not stationary. They're jostling around. They're vibrating. They're doing all kinds of things like that. But they're not totally free to move like the molecules in the liquid. And so as a result, the liquid's going to have a higher heat capacity. So it's negative, all right? And there's our temperature difference. And so when we do the calculation, we get this value here, negative 5.82 times 10 to the 3rd joules per mole. Great. All right. It's not hugely different from 6008, but it is different, and it is a more rigorous result than just assuming that that the enthalpy was independent. Enthalpy change was independent of temperature. All right. So now we're ready to go ahead. It's easy now to just calculate the entropy change for the surroundings. We're going to take our value here and plug it into our equation for delta H. Again, it's negative, right, of the delta H for the system. It's an exothermic process for the system. It's going to be an endothermic process for the surroundings. So we have a negative of a negative, which is a plus, divided by our temperature, which is 268, and this is the number we get. Positive 21.7 joules per Kelvin per mole, and it is positive, which was what we'd expect because we're dumping heat into the surroundings, so we expect the entropy of the surroundings to increase. And so just going ahead and continuing from that, we have our situation here, which shows that we add the result that we got for our system, all right, is negative 21.3. Here's our surroundings. We add the two together, and we get a positive 0.40 joules per Kelvin per mole. That's great, all right. It is positive. That means the entropy change for the universe greater than 0. We have not violated the second law. The freezing will be spontaneous. It is a small number, but that doesn't matter. When we talk about the second law, all that matters is it's greater than 0. It doesn't matter how much greater than 0 it is. It just matters that it is greater than 0. Because it's greater than 0, we know that will be the spontaneous process. So yay! We haven't found, or maybe not, maybe you wanted to find a violation of the second law, get the Nobel Prize for that, but no. We haven't found a violation of the second law here, so that's how we do that calculation. Now later on, we'll show how we can use delta G to do these calculations, and we won't have to calculate delta S for the surroundings. But nonetheless, we've shown that this freezing of the supercooled water, which happens irreversibly, is not a violation of the second law of thermodynamics. So that's how we do that calculation. So we'll see you on another day. Enjoy.